Put your hand flat against the wall beside you. It will not go through, and physics has a clean explanation for why. You do not have enough energy to cross a barrier that tall, and in classical mechanics, that settles the matter. Over the top, through a hole, or nowhere at all. But here is what nobody told you. That rule is not a law of nature. It is an approximation that holds only because you are large. Shrink the object, and it fails constantly, roughly 10 to the 19th times a second inside your own body, and 10 to the 38th times a second in the core of the Sun, where protons carrying 1,000th of the energy they need are fusing anyway. Without that failure, the sky is dark. This planet is frozen, and nothing here is alive to notice. By the end of tonight, you will know exactly what that loophole is, and why, after 94 years, nobody can tell you what happens inside the wall. Before we begin, if questioning reality this slowly is how you like to drift off, a quick like or subscribe really helps the channel grow. It is a small thing for you, and it means a great deal to me. Now, let's ease in. There is a wall somewhere near you right now. It might be an arm's length away, or across the room, or directly behind your head. Whatever it is made of, plaster, brick, timber, glass, you have never once in your life had to think about whether it would hold. You have leaned on walls, hung things from them, slept beside them, and never entertained the possibility that any part of you might end up on the other side without a door being involved. That confidence is not naive. It is one of the most thoroughly tested beliefs a human being can hold. Every single time it has been checked, by every person who has ever lived, the wall has won. And that confidence is built on a rule. The rule is simple enough that most people absorb it before they can articulate it, and it is taught formally, with equations attached, to every student who takes a physics class. The rule says this: to get from one side of a barrier to the other, you need enough energy either to go over the top of it or to break through it. There is no third option. Consider the cleanest possible version of the situation. Imagine a tennis ball rolling back and forth inside a box with perfectly frictionless walls and a perfectly frictionless floor. The ball rolls to one wall, bounces, rolls back across, hits the other wall, bounces again. Because nothing removes energy from the system, this continues without end. The ball has a certain amount of kinetic energy, and the walls are a certain height, and as long as the walls are taller than the ball's energy can carry it, the ball is going to stay in that box forever. There are exactly two ways for it to leave. Someone can pick it up and place it outside, adding energy from outside the system. Or the ball can be given enough speed that it clears the rim. That is the entire list. Physicists have a name for the place where the ball has to turn around. It is called the classical turning point. It is the position at which all of the ball's kinetic energy has been converted into potential energy against the barrier, and its speed has fallen to zero. Push past that point, and the arithmetic goes strange. To be further into the barrier than the turning point, the ball would need to have negative kinetic energy, and kinetic energy is 1/2 of the mass multiplied by the velocity squared. Mass is positive. A squared number is positive. There is no velocity, real or imagined, that makes that expression come out below zero. So the region beyond the turning point is not merely difficult to reach. It is not a place where the ball would need to be lucky, or fast, or persistent. It is a region that the mathematics of classical physics does not describe at all. The ball cannot be there in the same way that a number cannot be blue. You already trust this rule completely, in more contexts than you would guess. It is why a safe protects the things inside it. It is why a locked door means something. It is why a cell membrane can hold a chemical gradient in place, why a dam holds back a reservoir, why a thermos keeps coffee hot for hours. Every container that has ever contained anything is a bet on that rule. and the bet has always paid. It is worth pausing on one detail before we go on, because it widens the story considerably. When a physicist says barrier, they do not necessarily mean a wall. A barrier is anything that costs energy to cross. Two magnets pushed North Pole to North Pole are separated by a barrier, and you can feel it in your hands as you press them together. A chemical reaction that needs heating before it will start has a barrier in it. A ball at the bottom of one valley, with a hill between it and the next valley, is sitting behind a barrier made of nothing but landscape, and two positively charged particles approaching each other are climbing a barrier made purely of electrical repulsion, with no physical object involved anywhere. That last one is going to matter enormously later tonight. For now, just hold the idea that a barrier is a shape in the energy of a situation, not a thing you can touch. I want to state the rule as strongly as I can, because in a few minutes I am going to take it apart, and the taking apart only means something if we agree first on how solid it looks. Here it is at full strength. In classical physics, an object with less energy than a barrier requires will never, under any circumstances, no matter how many attempts it makes, no matter how much time passes, appear on the far side of that barrier. Not rarely, not once in a trillion tries, never. The probability is not small, it is exactly zero. That rule is wrong. It is not wrong in some technical, hair-splitting, only matters to theorists way. It is wrong in a way that has been measured in laboratories since the 1920s, exploited commercially in devices manufactured by the billion, and photographed at atomic resolution. And it is wrong in a way that has a consequence I suspect almost nobody listening has ever been told, which is this. If that rule were true, if barriers really were the absolute prohibitions that classical physics says they are, the sun would not shine, not dimly, not slowly, it would not shine at all. There would be no sunlight, no warmth reaching this planet, no photosynthesis, no food chain, no oxygen, no you. The failure of the rule you have trusted your whole life is the reason there is anything alive on Earth to trust it. The effect responsible is called quantum tunneling, and before we go any further, I want to apologize for the name on behalf of physics. It is a bad name. Nothing tunnels. There is no tunnel. Nothing bores a passage. Nothing squeezes through a gap. Nothing slips between the atoms of the wall. The word arrived in the 1920s as a rough translation of the German tunnel effect, and it stuck because it gives people a picture, going through the mountain rather than over it, and a wrong picture is easier to remember than no picture at all. I will keep using the word, because everyone else does, and because we need something to call it. But hold the image loosely. By the end of tonight, I am going to take that image away from you, and I am not going to be able to replace it with a better one, because nobody has one. Here is where we are going. We are going to find out what a particle actually is, which turns out to be nothing like a ball. We are going to solve the problem of that ball in that box properly, using the mathematics that actually describes matter, and watch a loophole open that classical physics said could not exist. We are going to work out exactly why that loophole never opens for you, and why it opens constantly for an electron. We are going to follow the effect into the core of the sun and see the thousandfold energy shortfall that should have left this solar system dark and frozen. We are going to find the same effect running inside your own cells while you lie there, and inside the phone charging beside you, and in the smoke detector on your ceiling. And then, at the very end, we are going to run into something I find harder to sit with than any of it. Because for all that we can measure this process, engineer it, predict its rate to extraordinary precision, and stake the existence of life on it, there are two very simple questions about quantum tunneling that physics cannot answer. Not has not answered yet, cannot. And the fact that the most important process in the universe is also one of the least understood is, to me, the strangest thing in this whole story. But we cannot get there from here. Not yet. To see the crack in the wall, you first have to stop believing in the ball. The trouble with the tennis ball in the box is not the box, it is the ball. In 1924, a French aristocrat named Louis de Broglie submitted a doctoral thesis containing an idea so slight on paper and so enormous in consequence that his examiners were not entirely sure what to do with it. Physicists had recently been forced to accept that light, which everyone knew was a wave, sometimes behaves like a stream of particles. De Broglie asked the obvious question in reverse. If a wave can behave like a particle, can a particle behave like a wave? And he wrote down a relation to go with the question. The wavelength associated with any object is equal to Planck's constant divided by that object's momentum. That is the whole idea. One line. His examining committee, uncertain, sent the thesis to Albert Einstein for an opinion. Einstein read it and wrote back that de Broglie had lifted a corner of the great veil and that the idea was more than a mere analogy. De Broglie got his doctorate. 5 years later, he had a Nobel Prize. Then, in 1927, at Bell Telephone Laboratories in New York, Clinton Davison and Lester Germer settled the question by accident. They were firing electrons at a nickel target when a laboratory accident, a broken vacuum flask, forced them to heat the nickel to clean it, which recrystallized it into large ordered domains. When they resumed the experiment, the electrons scattered off the crystal in a pattern of peaks and troughs. That is not what particles do, that is what waves do when they diffract. And when Davison and Germer measured the spacing of those peaks and worked backwards to a wavelength, the number that came out matched de Broglie's formula. Electrons are waves. This was not a philosophical position. It was a measurement, made with a broken flask and a piece of nickel. De Broglie's formula also quietly explains why nobody had noticed any of this before. Divide Planck's constant by momentum, and the answer for an everyday object is absurdly small. Planck's constant is about 6.6 times 10 to the minus 34 joule-seconds, a number with 33 zeros after the decimal point before the first meaningful digit. A tennis ball, traveling at 20 meters per second, has a wavelength of roughly 10 to the minus 34 meters. For comparison, a proton is about 10 to the minus 15 meters across. The ball's wavelength is smaller than the proton by 19 orders of magnitude, which is roughly the ratio between a human hair and the distance to the nearest star. There is no experiment, no apparatus, no conceivable arrangement of matter that could ever reveal a wave that small. The tennis ball genuinely is a wave. Its wave nature is simply irrelevant at every scale a human being can interact with. Do the same calculation for an electron, though, and the picture changes completely. An electron with a modest amount of energy, the sort you would find inside an atom, or in a wire, or in the plasma at the center of a star, has a wavelength of around 1/10 of a nanometer. That is the same size as an atom. It is the same size as the spacing between atoms in a crystal. It is the same size as the barriers it is going to meet. For an electron, the wave is not a hidden technicality. The wave is the whole story, and everything the electron does happens on a scale where the wave is as big as the obstacles. Meanwhile, over the Christmas holiday of 1925, Erwin Schrödinger had taken himself to a villa in the Swiss Alps at Arosa and come back with an equation. Across 1926, he published it in 4 papers in the Annalen der Physik, and it remains, a century later, the central equation of the physical world. It is the equation that tells you how the wave associated with a piece of matter behaves. I am not going to write it out, because this is not that kind of show, and you may well be lying down with your eyes closed. But I do want to tell you what it says in words, because the shape of it matters for everything that follows. The equation has 3 pieces. On the left there are 2 terms. The first is a kinetic energy operator acting on the wave. The second is a potential energy operator acting on the wave. On the right is the total energy multiplied by the wave. Kinetic plus potential equals total. If that sounds familiar, it should. It is conservation of energy, the same principle you learned with pendulums and roller coasters. Schrödinger's equation is that old, comfortable, entirely classical statement, rewritten so that it applies to a wave instead of to an object. That single substitution is where all of this begins. Everything strange that follows tonight comes from replacing a thing that has a position with a wave that has a shape. The wave itself is written with the Greek letter psi, and for a while, nobody, including Schrödinger, was certain what it represented. He initially hoped it might be a description of the actual physical spreading of charge, that an electron might really be a little smeared cloud of stuff. That interpretation failed almost immediately, because the wave spreads out over time in ways electrons demonstrably do not. The answer came from Max Born in 1926, and it arrived in one of the most consequential footnotes ever written. Born was working on collision problems, and in a paper on the quantum mechanics of scattering, he added a note, in proof, proposing that the squared magnitude of the wave function at any point gives the probability of finding the particle at that point. The wave is not made of matter. The wave is made of probability. That footnote is what converts Schrödinger's equation from elegant mathematics into physics, and it is the reason Born received the Nobel Prize in 1954, 28 years after he wrote it. Now sit with what that actually means, because people nod along to this sentence far too quickly. It does not mean that the electron is somewhere definite, and we happen not to know where. That would be ordinary ignorance, the kind you have about a coin under a cup. It means that having a definite position is not a property the electron possesses. What the electron has is a wave function, spread through space, and what a position measurement does is produce a location, one location, drawn from a distribution. Before that measurement, there is no fact of the matter about where it is. In the same way, there is no fact of the matter about which face a coin is showing while it is still in the air, except considerably more so, because the coin at least has faces. Werner Heisenberg formalized part of this in 1927, and Earl Kennard gave it its rigorous form as an inequality the same year. The uncertainty principle states that the uncertainty in a particle's position, multiplied by the uncertainty in its momentum, cannot be smaller than the reduced Planck constant divided by 2. Almost everyone first encounters this as a statement about clumsy measurement, that looking at a particle disturbs it. That is not what it says. It says that a state possessing both a perfectly sharp position and a perfectly sharp momentum does not exist. Not that we cannot find it, that there is no such thing to find. While we are here, let me kill a misconception you will meet everywhere, including in most popular explanations of tonight's subject. You will often hear that a tunneling particle briefly borrows energy from the vacuum using the uncertainty principle, sneaks through the wall, and pays it back on the other side. It is a vivid picture, and it is not how the mathematics works. Nothing is borrowed. Nothing is repaid. As we will see shortly, a particle that tunnels through a barrier comes out the other side with precisely the energy it went in with, down to the last decimal place. Energy conservation is not bent, suspended, or briefly overdrawn. It holds exactly. The strangeness of tunneling has nothing whatsoever to do with cheating on energy, which is what makes it so much stranger than the popular version. Here is the consequence I actually want you to carry into the next part. If a particle is described by a wave function, and if that wave function tells you the probability of finding it in any given place, then you have to ask where the wave function stops. And the answer, in the idealized mathematics, is that it does not. Solve the equations for an electron confined in a box, and you do not get a wave that is neatly zero everywhere outside the box. You get a wave that is very large inside the box and extremely small outside it. And the extremely small part keeps going. Out through the walls, out through the room, out past the building, past the atmosphere, past the orbit of the moon. So while you sit there, entirely reasonably, believing that the electrons in the wall beside you are in the wall beside you, the mathematics says something else. It says that each of those electrons has a non-zero probability of being detected on Mars. The number attached to that probability is so small that writing it down would waste more paper than it is worth, but it is not zero. And the difference between very small and zero is not a technicality. It is the entire subject of tonight. Take a moment and let the room around you change shape a little. The floor, the ceiling, the shelf, the fabric against your skin. Everything you can see and touch is a region where certain probability distributions happen to be very large. Nothing has a hard edge. Nothing has a definite boundary. The apparent solidity of the world is a statistical statement about where things are overwhelmingly likely to be found, and overwhelmingly likely is not the same as certain. Which brings us to the interesting question: what happens when one of these waves runs into a wall? Let us set the problem up properly, in the simplest form that still contains everything interesting. Picture a barrier. It has a height, which physicists call V0, and it has a thickness, which we will call L. On one side of it there is a particle, an electron say, approaching with a certain total energy, E, and the whole point of the exercise is that E is less than V0. The electron does not have enough energy to get over the barrier. In the classical picture we spent the first part of tonight admiring, that is the end of the story. The electron reaches the turning point, stops, and comes back. Now solve the same situation with Schrödinger's equation instead, and the barrier splits the world into three regions. In the first region, in front of the barrier, the electron's energy is greater than the potential, and the solution to the equation is a familiar oscillating wave. It rises and falls with a regular wavelength, traveling forward. Nothing surprising. This is the wave nature we established in the last part, doing exactly what a wave does. Then the wave reaches the barrier, and inside the barrier, the mathematics changes character entirely. This is the crucial moment, so let me be precise about it. Inside the barrier, the electron's energy is less than the potential, the same condition that made the classical arithmetic collapse. In Schrödinger's equation, that condition does not produce nonsense. It produces a different kind of solution. The oscillation stops. There is no wavelength anymore, no rising and falling, no crests and troughs. What remains is a smooth, real exponential decay, dropping away with distance into the barrier at a rate governed by a quantity physicists call kappa. Kappa is worth knowing in words because it contains the entire behavior of the effect. Kappa is the square root of the following: 2 multiplied by the mass of the particle multiplied by the amount of energy the particle is short by, the gap between the barrier height and the particle's energy, all divided by the reduced Planck constant. 3 ingredients: mass, energy shortfall, and a constant so small that it makes everything else enormous by comparison. Now here is the part that matters, and I want you to picture it as clearly as you can. Imagine you can ride along the wave function as it meets the barrier. In front of the wall, everything is ordinary. The wave rolls forward, rising and falling, with a wavelength about the width of an atom. Then the wall begins. The rolling stops instantly. The wave does not crash, does not reflect entirely, does not stop. It flattens into a smooth downward curve and begins to fall away, and it falls with terrible speed. Across the first atomic layer of the barrier, the height of the wave drops by a large fraction. Across the second, it drops by the same fraction again. Across the third, again. This is what exponential decay looks like from the inside. Not a slope, but a collapse. Each step down as savage as the one before, so that after only a few atomic diameters, the wave is 100 times smaller, then 10,000 times smaller, then a millionth of what it was. Keep going, and the numbers become ridiculous. But watch what does not happen. It does not touch zero. It cannot touch zero. An exponential curve approaches zero and never arrives there, no matter how far you carry it. And that mathematical fact, a fact about the shape of a curve, is the entire loophole. The wave function is smaller than anything you can easily name. It is still there. And then the far edge of the barrier arrives, and the wall ends, and the potential drops back down, and the mathematics changes character one more time. On the far side, the solution goes back to being an oscillating traveling wave, the same shape it had before, the same wavelength, traveling in the same direction. There is only one difference. Its amplitude is whatever tiny value the decay had reached by the time the wall ran out. Since probability is the square of the wave function's magnitude, a small amplitude on the far side means a small probability of finding the electron there. Small, not zero. Point a detector at the far side of that barrier, and every so often, perhaps once in 100 attempts, perhaps once in 1,000,000,000, depending on the numbers, it will register a particle that, by the rules of classical physics, has no business existing there. The wall is not solid to a wave. That is the sentence I want you to keep. The wall stops a ball absolutely and stops a wave only partially, and matter is not made of balls. Now let us look at that exponent, because everything that happens for the rest of tonight is a consequence of what lives inside it. The probability of transmission is dominated by a term of the form e raised to the power of -2 times kappa times the thickness of the barrier. Three quantities sit in there. The first is the thickness of the wall. The second is how far short of the barrier top the particle's energy falls. The third is the particle's mass, tucked under a square root. An exponent behaves nothing like an ordinary factor, and this is where intuition fails people most often. If a process depended on barrier width in a simple, proportional way, halving the width would double the odds. That is not what happens here. Because the width sits in the exponent, halving it can improve the odds by a factor of 1,000 or 1,000,000,000 or more, depending on where you started. Run it the other way, and the collapse is just as violent. Add a single extra atomic layer to a barrier, and the transmission probability can fall by a factor of 10. Add 10 layers, and you have divided the odds by 10 billion. Let me put a number on that with a real case, because the abstraction is doing a lot of work. Take an electron facing a barrier 1 nanometer thick, about 4 atoms of silicon laid end to end, with an energy shortfall of a few electron volts, which is the sort of arrangement you would find at the gate of a transistor. The transmission probability comes out somewhere in the region of 1 in 100,000. That sounds hopeless until you remember what an electric current actually is. A modest current through a wire carries something like 10 to the 18 electrons past a given point every second. 1 in 100,000 of 10 to the 18 is 10 to the 13. 10 trillion electrons per second, arriving somewhere they cannot classically reach. This is why an effect with fantastically small odds can nonetheless dominate the behavior of a device. The odds are being played an unimaginable number of times per second, and they are being played by objects that never get tired and never stop trying. Now thin that barrier from 1 nanometer to half a nanometer. The probability does not double from 1 in 100,000 to 1 in 50,000. It rises to something like 1 in 300. Halving the wall did not halve the difficulty. It removed almost all of it. And that single sentence is, as we will see later tonight, the reason the semiconductor industry hit a wall of its own in the early 2000s and had to rebuild the transistor from the materials up. There is a second, gentler term in front of the exponential, a prefactor built out of the particle's energy and the barrier's height. But it is a number of order 1, a factor of 2 here, or a factor of 5 there. It never changes the answer in any way that matters. The exponent is the whole story. Everything else is rounding. This is why quantum tunneling looks like two completely different phenomena, depending on where you meet it. In the subatomic world, it is not rare. It is constant, ordinary, the dominant behavior, happening so often that whole branches of physics and engineering are built on it. In your world, it is not merely rare. It is absent. Same equation, same three variables. The only thing that has changed is the numbers you feed into the exponent, and an exponent is a machine for turning modest differences into unbridgeable ones. Before we work out exactly where you sit on that scale, I want to close one door firmly, because the misconception behind it is everywhere. Quantum tunneling does not violate the conservation of energy. Measure the particle before it approaches the barrier, and measure it again after it has appeared on the far side, and its energy is the same. It has not gained anything. It did not borrow. It did not briefly become more energetic and then hand the excess back. The particle is on the other side of a barrier. It never had enough energy to cross, and it still does not have enough energy to cross it. And if you sent it at the same wall again, it would probably fail. Nothing about the energy books has changed. What has changed is our assumption that getting to the other side requires crossing. If you want to see this happen with something other than an electron, you can. It is a standard optics demonstration. Shine a beam of light inside a glass prism at a shallow enough angle, and it undergoes total internal reflection. All of it bounces back, none escapes. Now bring a second prism very close to the first, without letting them touch. Light appears in the second prism. Move the prisms slightly further apart, and the transmitted light falls away exponentially. It is called frustrated total internal reflection. It has been known since Newton, and it is the same mathematics with light standing in for matter. You can do it on a bench with two lumps of glass. So the effect is real, the mathematics is ordinary, and the demonstration is available to any undergraduate. Which raises a fair question, and it is the one everybody asks. If particles can appear on the far side of walls they cannot cross, why has nobody, in the whole history of the human species, ever walked through one? Let us actually do the calculation on you. Not on an electron, on your hand, resting on the covers, and the wall on the other side of it. Remember the three ingredients in the exponent: mass, under a square root, energy shortfall, barrier thickness. We will take them one at a time, and I would like you to keep a running tally in your head, because the tally is the point. Start with mass. An electron has a mass of about 9.1 times 10 to the minus 31 kilograms. Your hand has a mass of somewhere around half a kilogram. The ratio between them is roughly 5 times 10 to the 29th. 500,000 trillion. Mass enters the exponent under a square root, which sounds like it should help, and it does help, in the way that a discount of 99% helps when the price is the national debt. The square root of 5 times 10 to the 29 is about 7 times 10 to the 14th. So before we have considered anything else, the exponent for your hand is already 700 trillion times larger than the exponent for an electron. Now the thickness. An electron in a transistor faces a barrier about a nanometer across. Your hand faces a wall perhaps 10 centimeters thick. That is 100 million times further. Thickness sits in the exponent as a straightforward multiplier, so multiply again, 700 trillion times 100 million. And then the energy shortfall, which for a hand pressed against a solid wall is not a few electron volts, but the entire electromagnetic repulsion of every atom in your skin against every atom in the plaster, summed over something like 10 to the 24th atoms. The exponent that comes out the far end of that is not a number you can hold in your head. It is not 10, or 100, or 1,000. Careful estimates put it in the region of 10 to the 35th, a 1 followed by 35 zeros, and that is the number that goes into the exponent, not the answer. The answer is e raised to the negative power of that. Written as a decimal, the probability would begin with a decimal point, followed by more zeros than there are grains of sand on Earth, more zeros than there are stars in the observable universe, more zeros than there are atoms in your entire body, before you reach the first digit that was not a zero. You will sometimes see a much friendlier figure quoted in popular accounts, a probability of around 1 in 10 to the 40th for a person to tunnel through a wall. I want to be honest about that number, because it is far too generous, and generosity here is misleading in an interesting way. 1 in 10 to the 40th is a small chance, but it is a chance of the sort the universe deals in. 10 to the 40th attempts is a lot of attempts, but it is not an inconceivable number of attempts. You could imagine a very patient civilization getting there. The real figure is not in that neighborhood, or any neighborhood adjacent to it. There is no number of attempts that helps. There is no length of time that helps. If every particle in the observable universe attempted the crossing once per Planck time, the shortest interval that means anything, about 10 to the minus 43 seconds, for a trillion times the current age of the universe, the expected number of successes would still round to zero, and keep rounding to zero no matter how many decimal places you allowed yourself. Statistically impossible, not physically impossible. Hold on to that phrase, because I am going to hand it back to you at the very end of tonight, attached to something considerably larger than your hand. There is a version of this that most people already carry around, and it comes from fiction. Anyone who has read the books or seen the films knows the scene at King's Cross Station, where a character walks at a brick pillar between platforms 9 and 10 and passes straight through it. It is presented as magic, and it works as a scene precisely because everybody in the audience knows, without being told, that this is the one thing that cannot happen. What is quietly remarkable is that quantum mechanics does not forbid it. It assigns it a probability. The probability is the one we just calculated, which is to say, it is the most emphatic no that arithmetic can produce, without saying no. But the physics does not say the barrier is impassable. It says the barrier is passable, and the odds are these. That is a genuinely different kind of statement, and the difference is the reason we are here tonight. But probability is only the first reason, and honestly, it is the less interesting one. There is a second reason you do not tunnel, and it is independent of the arithmetic, and it is stronger. To tunnel, an object needs a wave function, a single, coherent, well-defined quantum description of itself. An electron in a vacuum has one. Your hand does not. Your hand is in constant, ceaseless interaction with its surroundings. Air molecules striking it billions of times per second. Infrared photons leaving it and arriving at it. The covers touching it. The electromagnetic fields of everything nearby reaching into it. Every one of those interactions is, in effect, a measurement. Every one of them entangles some part of your hand with some part of the outside world, and in doing so, it destroys the delicate phase relationships that make quantum behavior possible. That process is called decoherence, and it is savagely fast. For an object the size of a dust grain, in air, at room temperature, coherence survives for something like 10 to the minus 31 seconds. For a hand, it is unimaginably faster still. Your hand is not a quantum object that is very unlikely to tunnel. Your hand is not a coherent quantum object at all, at any moment, ever. It is continuously being observed by the universe, and an object under continuous observation does not get to be in two places. So the honest summary is that there are two locks on that door, and they are different kinds of lock. One is a probability so small, the word small has stopped meaning anything. The other is that the thing which would have to tunnel does not exist in the required state in the first place. Where does the boundary between those two worlds actually sit? This turns out to be one of the most interesting experimental questions in physics, and the answer keeps moving. In 2019, a group in Vienna sent molecules of more than 25,000 atomic mass units, assemblies of around 2,000 atoms, through an interferometer and observed interference fringes. Those are objects you could, in principle, see with a good enough microscope, and they were behaving as waves. In 1985, Michel Devoret, John Martinez, and John Clark demonstrated something stranger still: quantum tunneling in a superconducting circuit, where the thing doing the tunneling was not a particle at all, but the collective electrical phase of an entire macroscopic device. Billions upon billions of electrons, behaving as one coordinated quantum variable. It worked because they cooled the circuit to near absolute zero and isolated it obsessively from its environment, which is to say, they defeated decoherence rather than probability. It is worth noticing what those two experiments have in common, because it is not what people expect. Neither of them beat the odds. The Vienna molecules were not unusually likely to interfere. They were unusually well isolated, sent through a vacuum chamber cooled and shielded, so that nothing touched them on the way. The superconducting circuit was not unusually light. It was unusually undisturbed, held within a whisker of absolute zero inside layers of magnetic shielding. In both cases, the experimenters did not make the quantum behavior more probable. They simply stopped the environment from noticing. That is the pattern. The wall between the quantum world and yours is not a wall of size. It is a wall of isolation. Keep something cold enough and separate enough from everything else, and it will behave as a wave, regardless of how large it is. None of which is going to get you through the plaster tonight. The door is locked, but I want to be precise about the kind of locked it is, because the distinction turns out to matter enormously. It is not locked in the way that dividing by zero is forbidden, or the way that a square circle is forbidden. Those things are not merely unlikely, they are incoherent. This is not that. There is a number attached to you walking through that wall, and the number is not zero, and physics is completely comfortable with the idea that it could happen. It simply will not. So the effect is real, and it is closed to you. Which means the interesting question is not whether it happens, it is where it happens often enough to matter. And the answer to that turned up in 1928, in a problem that had been embarrassing the most famous physicist alive for 17 years. The first person to notice tunneling in the wild was not looking for anything so dramatic. He was trying to understand the shape of a molecule. In 1927, Friedrich Hund was working through the quantum mechanics of molecules with two equivalent configurations, a situation physicists call a double well, because the energy landscape has two valleys with a hill between them. The particular molecule that makes this vivid is ammonia. An ammonia molecule is a nitrogen atom sitting above a triangle of 3 hydrogen atoms, like the apex of a very squat pyramid. There are 2 equally valid arrangements, the nitrogen above the triangle or the nitrogen below it. To get from one to the other, the nitrogen has to pass through the plane of the hydrogens, and passing through that plane costs energy the molecule does not have. By the classical rules, an ammonia molecule should pick a side and stay there forever. It does not. The nitrogen atom flips from one side to the other, back and forth, about 24 billion times every second. It does not go over the barrier, it goes through it, at a rate so fast and so regular that the ground state of the molecule is best described not as up or down, but as both at once. That flipping rate turned out to be so stable and so precisely reproducible that in 1949, the National Bureau of Standards in the United States built the world's first atomic clock around it, the first clock in history to keep time by something more reliable than the rotation of the Earth, kept time by counting a quantum tunneling event. Nobody mentions this when they talk about atomic clocks. I find it a lovely piece of history. But the discovery that made tunneling undeniable came the following year, from a scandal that had been sitting in nuclear physics since 1911. In that year, Hans Geiger and John Nuttall published a relationship between two things that ought to have been only loosely connected: the energy of the alpha particle a radioactive nucleus emits, and how long that nucleus takes to decay. What they found was not a gentle trend. It was a cliff. Here are the two ends of it. Thorium-232 emits an alpha particle carrying about 4.08 mega-electron-volts of energy, and it has a half-life of 14 billion years, longer than the current age of the universe. Polonium-212 emits an alpha particle carrying 8.78 mega-electron-volts, and it has a half-life of about 3/10 of a microsecond, slightly more than double the energy, 24 orders of magnitude faster, a factor of a million. Nothing in classical physics does that. Classical processes are polite. Double an input and outputs change by factors of 2, or 4, or 10. To get 24 orders of magnitude out of a factor of 2, you need something exponential sitting underneath, and in 1911, nobody had any idea what it might be. Then it got worse, and the person it got worse for was Ernest Rutherford, the man who had discovered the nucleus in the first place. Rutherford's own scattering experiments had established the height of the electrical barrier surrounding a heavy nucleus. Fire alpha particles at uranium, with energies approaching 9 mega-electron-volts, and they are turned back. The Coulomb repulsion of all those protons pushes them away before they can reach the nucleus. So the barrier around a uranium nucleus is at least 9 mega-electron-volts tall. That is a measurement, not a theory. And yet uranium emits alpha particles. Routinely, constantly. It has been doing it since before the Earth formed. And the alpha particles that come out are carrying about 4.2 mega-electron-volts. Sit with that for a moment, because it is genuinely absurd. Particles are escaping from inside a container whose walls are more than twice as tall as the particles are energetic. It is a ball climbing out of a bowl it cannot see over. Rutherford, to his credit, knew it made no sense, and he floated a rescue. Perhaps the alpha particle drags a couple of electrons along with it, neutralizing some of its charge on the way out and lowering the effective barrier. Nobody found the idea convincing, including, one suspects, Rutherford. The answer came in 1928 from a 24-year-old Russian working in Göttingen named George Gamow. His paper on the quantum theory of the atomic nucleus in the Zeitschrift für Physik is short. Its argument is the one we built in the last two parts. The alpha particle is a wave. It is confined inside the nucleus by the Coulomb barrier. Its wave function decays exponentially through that barrier and emerges with a small but non-zero amplitude on the far side. The alpha particle never goes over the wall. It leaks. Almost simultaneously and entirely independently, Ronald Gurney and Edward Condon reached the same conclusion in Britain and the United States, publishing a short note in Nature in 1928 and a full treatment in the Physical Review the following year. When three people find the same answer at the same time from different directions, the answer is usually right. And here is what makes Gamow's explanation so satisfying. It does not merely permit alpha decay, it predicts the cliff, because the escape probability sits in an exponent, and because raising the alpha particle's energy shrinks the effective width of the barrier it has to penetrate. A modest increase in energy produces an enormous increase in escape rate. The 24 orders of magnitude that had been sitting in the data since 1911 were not a curiosity. They were the fingerprint of an exponential, printed across the periodic table, waiting 17 years for somebody to recognize the handwriting. The picture that comes out of the mathematics is worth holding on to, because it is the first time tonight we meet a theme that will return again and again. Inside a uranium nucleus, the alpha particle is rattling around, striking the inside of the Coulomb barrier, something like 10 to the 21st times every second. That is 1,000 million attempts per second. And on each attempt, the probability of getting through can be as small as 10 to the minus 38. Multiply those two numbers together, and you get a decay rate corresponding to a half-life of billions of years. The nucleus is not stable because nothing is trying to escape. It is stable because something is trying to escape constantly and almost always failing. Stability, at this level, is not the absence of an event. It is an event that is exceptionally rare and exceptionally persistent. That combination, an almost impossible process, attempted an almost unimaginable number of times, is going to be the engine of everything that follows. 1928 was, in retrospect, an extraordinary year for this one idea. In the same 12 months, and quite separately from the nuclear work, Ralph Fowler and Lothar Nordheim published a theory in the Proceedings of the Royal Society explaining how electrons escape from the surface of a metal when a strong electric field is applied to it. Their answer was the same answer. The field tilts the barrier at the metal's surface, thinning it, and the electrons tunnel out. That paper is now the foundation of the electron guns in electron microscopes and, as we will come to later tonight, of the way the phone beside you erases a file. Two groups, working on completely unrelated problems, arrived at the same mechanism within months of each other, which is usually a sign that a field has found something real. The people involved are worth a sentence, because the history of physics is rarely as tidy as it looks in textbooks. Gamow defected from the Soviet Union in 1933 after 2 failed escape attempts, one of which involved trying to paddle a kayak 250 kilometers across the Black Sea to Turkey with his wife. They were driven back by weather. He got out eventually, legitimately, through a conference in Brussels and never returned. Edward Condon, meanwhile, went on to chair the United States Air Force's official investigation into unidentified flying objects in 1968. An odd late chapter for a man who co-discovered why the sun burns. The confirmation arrived within 4 years, and it came from turning the argument around. Gamow visited the Cavendish Laboratory in Cambridge and pointed out the obvious corollary. If alpha particles can leak out of a nucleus, then particles can leak in. You should not need to accelerate a proton to the full height of the Coulomb barrier to make it react with a nucleus. A fraction of that energy should do, because the proton will tunnel the rest of the way. The reaction rate would be low, but low is not zero, and low can be measured. In 1932, John Cockcroft and Ernest Walton built a machine to test it. They accelerated protons through a few hundred kilovolts, roughly 1/10 of the energy classical physics said was needed, and fired them at a lithium target. Lithium-7 absorbed a proton and split into 2 alpha particles. It was the first time human beings had deliberately broken apart an atomic nucleus, and it worked only because the protons were doing something the previous generation of physics said was impossible. Cockcroft and Walton received the Nobel Prize for it in 1951. Look at how fast that happened. 1911, an unexplained cliff in the data. 1928, an explanation. 1932, a laboratory technique. Inside of 4 years, tunneling went from an outrageous theoretical proposal to a thing you could do on a Tuesday afternoon in Cambridge with a few hundred kilovolts and some lithium. And nobody, in all the years since, has found a reason to doubt it. This is not a frontier idea. It is not contested. It is 98 years old. It is in every undergraduate textbook, and it is the basis of industries. Which is why what happens next is so peculiar, because in that same window, physicists took the identical piece of mathematics, pointed it at the sky, and used it to answer a question that had been troubling astronomy for the better part of a century. Go to the center of the Sun. The temperature there is about 15.7 million Kelvin. The density is around 150 grams per cubic centimeter, which is roughly 13 times the density of lead, though it is not solid, or liquid, or gas. At that temperature, no atom survives intact. Every electron has been stripped from every nucleus, and what fills that space is a plasma, a fog of bare atomic nuclei and free electrons, compressed to 13 times the density of the heaviest metal you have ever held, and hotter than anything you will ever encounter. That is the environment. Now here is the number that matters. At 15.7 million Kelvin, the average thermal energy carried by a proton is about 1.35 kilo-electron-volts, 1,350 electron-volts. That is what a typical proton in the core of the Sun has to work with. And here is what it needs. 2 protons both carry positive charge, so as they approach each other, the electrical repulsion between them grows. To fuse, they have to get close enough for the strong nuclear force to take over and bind them together, and the strong force has an extremely short reach. It does essentially nothing until the 2 particles are within about 1 to 2 femtometers of each other, which is roughly the width of a proton. Climbing the Coulomb repulsion down to that distance costs energy. How much depends slightly on exactly where you decide the strong force switches on, and reasonable estimates run from several hundred kilo-electron-volts up to about 1.5 mega-electron-volts. Let us take 1 mega-electron-volt as the working figure. 1 million electron-volts required. 1,350 electron-volts available. The protons in the core of the Sun are short by a factor of about 1,000. I want to be clear that this is not a near miss. This is not a case where most protons fail and a few lucky ones scrape through. In classical physics, a factor of 1,000 in energy is an absolute prohibition, and there is nothing to discuss. The obvious rescue is statistics. Particles in a hot gas do not all have the same energy. They are spread across a distribution, with most near the average, and a thin tail running up to much higher energies. So perhaps the fusion is being done by the rare, unusually energetic protons in the tail. This is a good instinct, and it is the first thing anyone tries. It fails, and it fails so badly that the failure is worth appreciating properly. The high-energy tail of that distribution falls off exponentially. The fraction of protons carrying 1,000 times the average thermal energy is of the order of e to the minus 1,000. Written as a power of 10, that is around 10 to the minus 434. Now let us throw everything we have at that number. There are roughly 10 to the 57 protons in the Sun. The universe has existed for about 10 to the 17 seconds. Multiply every proton by every second since the beginning of time, and you get 10 to the 74. Against 10 to the minus 434, that is not a dent. It is not a rounding error. You could give the Sun 1 trillion universes worth of time, and 1 trillion suns worth of protons, and you would not get one single fusion event. So let me state the conclusion, in the plainest terms I can, on classical physics. Even classical physics with the full machinery of statistical mechanics behind it. The Sun is cold. It does not ignite. It never has. It is a large ball of hydrogen slowly cooling in the dark. And this solar system is a set of frozen rocks orbiting a dim, contracting sphere of gas. That is the universe classical physics describes. It is not the one we live in. What actually happens is a compromise between 2 exponentials running in opposite directions. As you look at higher energies, the number of protons available falls off exponentially. Fewer and fewer particles are that energetic. But as you look at higher energies, the probability of tunneling through the Coulomb barrier rises exponentially, because a more energetic proton faces a thinner effective barrier. One curve is collapsing, the other is climbing. Multiply them together and you get a sharp, narrow peak somewhere in the middle. an energy at which there are still enough protons to matter, and the tunneling odds have improved enough to matter. That peak is called the Gamow peak, named, of course, for the same Gamow, and the narrow band around it is the Gamow window. For proton-proton fusion, at the temperature of the solar core, it sits at about 6 kiloelectronvolts, in a window running roughly from 3 to 10. Every fusion reaction in the Sun that produces the light falling on this planet happens inside that narrow band, which means the protons doing the work are unusual by solar standards, carrying about 5 times the average thermal energy, and are still short of the classical requirement by a factor of roughly 200. They do not climb, they leak. Let me take you down there, because numbers on their own do not do this justice. Start at the surface, at the photosphere, where the temperature is a mild 5,800 Kelvin, and the gas is thinner than the air in this room. Below that is the convection zone, where the plasma boils in cells the size of Texas, each one rising, spilling over, and sinking again on a cycle of about 20 minutes. Keep going down. The convection stops, and the radiative zone begins, a region so dense and so opaque that light does not travel through it, so much as stagger, absorbed and re-emitted endlessly, wandering rather than moving. Down further, the density climbs, the temperature climbs, and then you are in the core, in the innermost quarter of the Sun's radius, where a third of its entire mass is packed, and where more than 99% of its energy is made. Now stop and watch 2 protons. They are approaching each other at enormous speed, and as they close, the repulsion between them builds. They slow, they keep closing, and they keep slowing, and the deceleration grows more violent as the distance shrinks. They reach the point where, by every rule you have ever been taught, they must stop and turn away from each other. Hold there. This is the classical turning point, and it is where the story is supposed to end, and it is still 10 femtometers, 5 proton widths, from where anything interesting could happen. And then, without anything crossing anything, they are bound. There is no moment of passage to observe, because there is nothing to observe. There is a before, in which 2 protons are approaching a barrier they cannot cross. There is an after, in which they are a single nucleus. A flash of energy is released as they settle. One of the 2 protons converts into a neutron, spitting out a positron and a neutrino, and that neutrino leaves the Sun in about 2 seconds, carrying the news outward at very nearly the speed of light, long before the light itself will manage the same trip. This happens, in the core of the Sun, somewhere on the order of 10 to the 38th times every second. There is one more thing making this improbable, and it is the reason we are here at all. Tunneling is not sufficient by itself. That first step of the chain requires a weak interaction event on top of the tunneling. One of the 2 protons has to convert into a neutron in the instant they are together, and the weak force is called weak for good reason. Take a single proton in the core of the Sun and ask how long it will wait before it undergoes its first fusion reaction, and the answer is measured in billions of years. The commonly quoted figure is around 9 billion. The Sun is 4.6 billion years old. Most of the protons in it have not reacted yet. Most of them never will. The result is a star that burns with something close to indifference. The Sun's total output is 3.828 times 10 to the 26th watts, which sounds like a great deal until you divide it by the Sun's volume. The average power density of the Sun works out to around 276 watts per cubic meter. A human body at rest produces about 100 watts in a volume of roughly 7/100ths of a cubic meter, well over 1,000 watts per cubic meter. Cubic meter for cubic meter, you are producing more heat right now than the core of the Sun. So is a compost heap. The Sun is not bright because any part of it is fierce. The Sun is bright because it is enormous. And that gentleness is not a curiosity. It is the whole reason there was time for anything to happen on this planet. A process this slow burns for 10 billion years. If fusion in the sun were easy, if protons could simply climb the barrier, the sun would have converted its hydrogen in a fraction of that and been gone long before the first cell divided. Tunneling makes fusion possible, and the exponential improbability of tunneling makes it slow, and the slowness is what buys 4.5 billion years of stable sunshine. Both halves of that matter equally. Run it the other way, and the point becomes stark. For the sun to fuse hydrogen by classical means, its core would need to be around 10 billion Kelvin instead of 10 million, 1,000 times hotter. Nothing the mass of the sun can reach that temperature. Gravity cannot compress it that far. Without tunneling, there is no minimum mass at which a ball of hydrogen becomes a star. There is simply no such thing as a star. Every second, the sun fuses about 600 million tons of hydrogen into roughly 596 million tons of helium. The missing 4.3 million tons per second is mass converted into energy, and that energy begins a long, slow escape. A photon released in the core does not fly out. It is absorbed and re-emitted over and over, stumbling through the radiative zone in a random walk. Estimates of how long that takes vary a great deal with the model. Figures anywhere from 10,000 to 170,000 years are defensible, and 100,000 is a common working number. Only after that does it reach the surface and cross 93 million miles of empty space, which takes 8 minutes and 20 seconds. So here is where all of this lands, and it is why I wanted to build the argument slowly. The warmth you have felt on your face on every sunny day of your life did not come from a process that classical physics finds difficult. It came from a process that classical physics forbids outright. Every calorie you have ever eaten traces back through a plant, through photosynthesis, to a barrier crossing that could not happen. Every fire that has ever been lit on this planet was burning stored sunlight from a reaction that should never have occurred. The oxygen in your lungs, the temperature of the ocean, the fact that water on this world is liquid rather than ice, all of it is downstream of protons arriving somewhere they could not reach. This is the reason life exists, not a contributing factor, not one condition among many. Without quantum tunneling, the sky is dark, the earth is frozen, and there is nothing here to notice. That is the first thing almost nobody has been told. There is a second, and it is stranger, but we are not ready for it yet. Let us stop for a moment and put the pieces we have on the table, because we are about halfway through, and it is worth seeing the shape of it before we go on. We started with a rule: barriers cannot be crossed without enough energy. We found that the rule was written for objects, and that matter is not made of objects, but of waves. We solved the barrier problem for a wave, and found that the wave does not stop at the wall. It collapses inside it, steeply, exponentially, and comes out the other side smaller but intact. We worked out that the collapse depends on mass, width, and energy shortfall, all sitting inside an exponent, which is why the effect is absent from your life and constant in the subatomic world. We watched physicists discover it in 1928 by explaining why uranium leaks. And then we took it to the center of the sun and found that the star holding this planet together runs entirely on a process that classical physics says is impossible. That is where we are. Now it gets more personal. Because the sun's light is only half of what the process gave you. The other half is the material you are made of. Hydrogen and helium were manufactured in the first few minutes after the Big Bang, and that is essentially the entire inventory the universe started with. Everything else, the carbon in your cells, the oxygen in your blood, the nitrogen in your DNA, the calcium in your bones, the iron carrying oxygen around your body right now, was assembled later, inside stars. And every single step of that assembly is a tunneling event through a Coulomb barrier that is higher than the one before it, because each new element has more protons and pushes back harder. The hardest step comes almost immediately, and it very nearly stops everything. To build carbon, you need to fuse 3 helium nuclei. The natural route is to do it in 2 stages. Fuse 2 helium nuclei to make beryllium-8, then add a third. The problem is beryllium-8. It is not stable. It falls apart with a half-life of about 8.2 times 10 to the minus 17 seconds, 82 quintillionths of a second. That is the window. In that sliver of time, a third helium nucleus has to arrive, tunnel through the Coulomb barrier, and fuse, or the whole thing comes apart, and you are back to helium. Edwin Salpeter worked out in 1952 that in a hot enough stellar core, an equilibrium population of beryllium-8 would persist, a tiny standing population, constantly forming and constantly decaying, but never quite zero. That helped. It was still not nearly enough. The calculated rate of carbon production fell far short of the amount of carbon that visibly exists in the universe, and in the bodies of the people doing the calculation. Fred Hoyle's response in 1953 is one of the boldest arguments anyone has made in physics, because he reasoned backwards from his own existence. His logic went like this: carbon exists. I am made of it. Therefore, the reaction that produces carbon must proceed far faster than our current numbers allow. The only mechanism that could speed it up by the required amount is a resonance, a previously unknown excited energy state of the carbon-12 nucleus, sitting at just the right energy to catch an incoming helium nucleus and hold it. And from the energies of the ingredients, that state must lie somewhere near 7.65 megaelectronvolts. He then went to Willie Fowler's group at Caltech and asked them to look for it. They did not want to. There was no theoretical reason to expect a state there, other than Hoyle's insistence that he existed. They looked anyway, largely to make him go away, and within months they found it, within a whisker of where he said it would be. The state is now measured at about 7.654 megaelectronvolts. It has been called the Hoyle state ever since. Now, the thing to understand about that resonance is that it does not replace tunneling. It multiplies it. The helium nucleus still has to penetrate the Coulomb barrier of beryllium-8. Nothing about a resonance changes the electrical repulsion between 2 positively charged objects. What the resonance does is make the fusion enormously more likely on the occasions when the tunneling succeeds. The barrier is still there. The leak is still the only way through. The resonance simply means that what leaks through sticks. The sensitivity of this arrangement is difficult to overstate. The triple alpha reaction rate scales roughly as temperature to the 40th power in the relevant range, because you are stacking 2 tunneling exponentials on top of one another. A 10% change in temperature changes the carbon production rate by a factor of around 40. Whether that also implies the resonance itself is finely tuned for life is a genuine and unresolved technical argument in physics, and I will leave it as one. Published estimates of how much wiggle room the Hoyle state has vary a great deal, and anyone who tells you the answer is settled is telling you about their philosophy rather than the data. After carbon, the chain continues. Carbon captures a helium nucleus to make oxygen, a reaction whose exact rate at stellar energies remains one of the largest sources of uncertainty in the whole of stellar modeling, which is a slightly uncomfortable thing to know about the atom you are breathing. Oxygen captures another to make neon, neon to magnesium, magnesium to silicon, silicon eventually to iron. Each step faces a taller barrier than the last, because the charges keep growing, and each step is a tunneling event. At iron, fusion stops paying. Fusing anything heavier than iron-56 consumes energy rather than releasing it, so no star can build past it in its core. Everything above iron on the periodic table, the copper in the wiring behind your wall, the silver, the gold, the iodine in your thyroid, the uranium in the ground, was made by a different mechanism entirely: neutron capture, in dying stars, and in the collisions of neutron stars. And neutron capture faces no Coulomb barrier at all, because a neutron has no charge and nothing pushes back. That contrast is worth noticing. Tunneling matters exactly and only where charge repels. Remove the repulsion, and the barrier vanishes, and so does the need for the loophole. There is a small piece of evidence for all this sitting in the cosmic abundances, and I like it because it is a gap rather than a presence. Lithium, beryllium, and boron, elements 3, 4, and 5, are anomalously rare in the universe, far rarer than the elements on either side of them. The reason is beryllium-8's instability. There is no stable stepping stone at mass 8, so stellar fusion simply skips over that stretch of the periodic table. Those three elements exist mostly because cosmic rays occasionally smash heavier nuclei apart in interstellar space. The instability that nearly prevented carbon left a visible hole in the universe's inventory, and we can see it in the spectra of stars. There is a loop worth closing here, because the elements the stars built went back into the stars and changed how they burn. Once carbon and nitrogen and oxygen exist in a stellar interior, they can act as catalysts for hydrogen fusion, a sequence called the CNO cycle, in which a carbon nucleus absorbs 4 protons one at a time, passes through nitrogen and oxygen, and eventually spits out a helium nucleus and the original carbon, ready to start again. Hans Bethe worked this out in a 1939 paper in the Physical Review that essentially founded the field of stellar energy production, and it earned him the Nobel Prize 28 years later. The CNO cycle contributes only about 1% of the Sun's energy, because carbon has 6 protons and nitrogen 7, so the Coulomb barriers are far higher and the tunneling probability far lower. But in stars much heavier than the Sun, it dominates completely, so the elements that tunneling built now govern how the next generation of stars burns, and they do it by presenting a taller barrier, which the same effect then has to overcome all over again. The full framework was laid out in 1957 in a paper by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, known ever since by the initials of its 4 authors, which remains one of the most cited papers in astrophysics. Fowler received the Nobel Prize for it in 1983. Hoyle did not, a decision that is still argued about, and which most people who know the history regard as indefensible. So take stock of what you are, materially. By mass, a human body is about 65% oxygen, 18% carbon, and 10% hydrogen. The hydrogen has been here since the first 3 minutes of the universe. The other 83% was assembled, atom by atom, inside stellar cores, by particles arriving on the far sides of barriers they could not cross. Every carbon atom in you passed through a beryllium nucleus that lasted less than a quintillionth of a second. Every oxygen atom in you was a carbon atom that got lucky. You are not merely warmed by a process classical physics forbids. You are constructed out of its output. And it is not finished with you. It did not stop when the star that made your atoms died. It is running inside your body right now, in every cell, several billion times a second, while you lie there doing nothing at all. Most people think of respiration as a kind of slow burning. You breathe in oxygen, you eat food, the food is oxidized, energy comes out. That description is true at the level of bookkeeping, and almost entirely wrong at the level of mechanism. What actually happens is that your cells strip electrons off the food you have eaten and then pass those electrons down a chain, one handoff at a time, releasing a small amount of energy at each step and using it to pump protons across a membrane. The pressure of those accumulated protons then drives a rotating molecular turbine that manufactures ATP, the molecule that powers essentially everything you do. It is not burning. It is an electrical circuit, built out of protein, and it is running in every cell in your body while you lie there. The chain lives in the inner membrane of your mitochondria, folded into tight pleats to maximize its surface area, and it is made of a series of large protein complexes. Inside those complexes, the electrons hop between metal centers and organic cofactors, iron-sulfur clusters, heme groups, copper atoms, quinones, each one holding the electron briefly before handing it on. And here is the problem that nobody mentions in a biology class. Between those centers, there is nothing. No wire, no conducting channel, no metallic pathway. The gap between one redox center and the next is filled with ordinary protein, chains of amino acids that are, electrically speaking, an insulator. The electron has to get from one side of an insulating barrier to the other, and it does not have the energy to cross it. It tunnels, every single time. The quantitative structure of this was worked out over 2 decades by Christopher Moser, Les Dutton, and their colleagues at the University of Pennsylvania, and their central result was published in a 1999 paper in Nature by Page, Moser, Chen, and Dutton. What they established is now known informally as Dutton's ruler, and it is exactly the exponential we have been carrying all night. Biological electron transfer rates fall by roughly a factor of 10 for every 1.7 angstroms of additional distance between the donor and the acceptor. An angstrom is a 10 billionth of a meter, about the radius of a hydrogen atom. Move 2 redox centers apart by less than the width of 2 atoms, and the rate drops tenfold. Then they did something clever. They surveyed the structures of every respiratory and photosynthetic protein complex that had been solved, and they measured the distances between consecutive redox centers. And what they found was a hard edge. Nature essentially never places consecutive centers more than about 14 angstroms apart. Not rarely, almost never. Beyond 14 angstroms, the exponential kills the transfer rate. The electron sits too long, the chain stalls, and the organism dies. Which means that 4 billion years of evolution, working with no theory and no equations, discovered the tunneling exponent and obeyed it. Every functioning respiratory chain on this planet is built to a specification set by a term in Schrödinger's equation. I want you to go inside one of these, because it is happening in you right now, and I think it deserves the attention. Pick a cell, one in your upper arm, resting against the mattress. Inside it, several hundred mitochondria. Inside one of those, the inner membrane, folded into ridges like a pleated curtain. Bolted into that membrane are the complexes, each one an assembly of thousands of atoms held in a precise arrangement. An electron arrives at an iron-sulfur cluster in the first complex. Ahead of it lies 14 angstroms of protein, a thicket of amino acid chains, carbon and nitrogen and oxygen, with no path, no channel, no opening. By every classical measure, it is a wall. The electron does not have the energy to cross it, and then it is on the other side, not moving across. There is no crossing to film, no trajectory to trace, no instant at which the electron is halfway. It is here, and then it is there, and the rate at which that transition happens has been tuned by evolution to a distance where the exponent still permits it. Then the next center, then the next complex, then oxygen at the end of the line, waiting to take the electron and combine with hydrogen to make water, which is where the oxygen you are breathing actually goes. Across your whole body, something on the order of 10 to the 19th of these transfers is happening every second. Your body synthesizes and consumes roughly its own weight in ATP over the course of a day, 50 to 70 kilograms of it, made and spent and made again, on machinery whose critical steps have no classical description. The simple warmth you feel under the covers is the aggregate waste heat of 100 trillion mitochondria running a process that should not work. Respiration is the best established case, but it is not the only one. Enzymes, the proteins that make biochemistry go fast enough to be alive, very often work by moving a hydrogen atom, or a proton, or a hydride ion, from one place to another. Hydrogen is the lightest nucleus there is, which puts it in a favorable position in the exponent. And for decades, there has been strong evidence that enzymes exploit that. The cleanest way to detect it is an isotope trick. Replace the hydrogen with deuterium, which is chemically identical but twice as heavy, and compare the reaction rates. If the reaction proceeds classically, over the top of the energy barrier, the ratio between the two rates has a ceiling, around 7 at room temperature, set by the difference in vibrational energies. If the reaction proceeds by tunneling, the ratio can be far larger, because the exponent contains mass, and doubling the mass is catastrophic for the odds. Soybean lipoxygenase, one of the most studied enzymes in this field, shows a kinetic isotope effect of around 80, not 7, 80, an order of magnitude above anything classical chemistry can produce. Judith Klinman and Amnon Cohen collected the evidence across dozens of enzyme systems in a review in the Annual Review of Biochemistry in 2013, and the conclusion is not controversial. Hydrogen tunneling in enzymes is standard biochemistry. There is even evidence that the proteins actively help. Certain vibrational motions in the enzyme, on picosecond timescales, appear to transiently squeeze the donor and acceptor closer together, thinning the barrier for an instant and boosting the odds. If that holds up in general, enzymes are not merely permitting tunneling, they are engineering it. Photosynthesis runs on the same physics from the opposite direction. When a photon is absorbed in a reaction center, the initial charge separation, pulling an electron away and handing it to an acceptor molecule, happens in a few picoseconds with a quantum efficiency close to 100%. Almost every photon that arrives results in a transferred electron, and electron tunneling is part of that chain. The sunlight that tunneling produced in the core of a star is captured, on this planet, by tunneling. I should mention one place where the field got ahead of itself, because intellectual honesty demands it. In 2007, a paper in Nature reported evidence of long-lived quantum coherence in a photosynthetic light harvesting complex, and for several years, this was widely reported as proof that plants use quantum computation to find the most efficient energy pathway. That claim has been substantially walked back. Later work attributed most of the observed oscillations to vibrations in the molecules rather than to electronic coherence, and the strong version of the story is no longer supported. Tunneling in photosynthesis is solid. Quantum computation in photosynthesis is not. And then there is one more, which is genuinely unsettled, and which I want to flag clearly as such, because it is the most dramatic claim in this whole area. In 1963, Per Olof Lurdin published a paper in Reviews of Modern Physics, pointing out something about the structure of DNA. The two strands are held together by hydrogen bonds, protons shared between base pairs, and a proton, being light, is an excellent candidate for tunneling. Lurdin proposed that a proton could occasionally tunnel across to the wrong side of its bond, producing what chemists call a tautomer, a rearranged form of the base that pairs incorrectly. If the strand is then copied before the proton tunnels back, the error is written into the daughter molecule as a permanent point mutation. If that is right, then quantum tunneling contributes to the spontaneous mutation rate, and therefore to the raw material of evolution itself. The same effect that lit the star that made your atoms would also be writing the occasional typo into your genome. The idea sat quietly for decades. In 2022, Louis Slocum, Marco Sacchi, and Jim Al-Khalili published open quantum system calculations in communications physics, arguing that the tautomer population in guanine cytosine pairs is far from negligible, of the order of 1 in 10,000, and that the proton transfer reaches equilibrium much faster than DNA is replicated. Whether that translates into a measurable mutation rate in a living cell is unresolved and actively disputed. Treat it as an open question with serious papers behind it, not as a settled fact. What is not in question is the underlying point. It is the same exponent, the same three variables, mass, width, energy shortfall, that we used on your hand and on a proton in the sun. The core of a star runs at 15.7 million Kelvin. Your mitochondria run at 37 degrees Celsius. The physics does not care. The barrier is thin enough and the particle is light enough, and so the leak happens in a plasma 13 times denser than lead and in the soft protein of your own chest by exactly the same mechanism. Which raises the obvious next question. If it is running inside you, what else is it running inside? For the semiconductor industry, quantum tunneling has two faces. It is the thing that nearly ended their business, and it is the operating principle of several of their most important products. I find that duality satisfying, and it is worth walking through both sides. Start with the trouble. A transistor is a switch. It has a source, where the electrons come from, a drain, where they go, and between them, a channel. Above the channel sits a gate, separated from it by a thin layer of insulator, and by putting a voltage on the gate, you create an electric field that either allows current to flow through the channel or shuts it off. That is the whole device, repeated by the tens of billions on a chip. Making transistors smaller means making the channel shorter, but a shorter channel is harder for the gate to control. And to keep control, the insulating layer under the gate has to be made thinner at the same time. For decades, the insulator was silicon dioxide, ordinary glass, essentially. And thinning it worked beautifully. It worked for so long and so reliably that the entire economics of the computing industry was built on the assumption that it would keep working. By the early 2000s, gate oxides in production were down to about 1.2 nanometers. That is roughly 5 atomic layers of silicon dioxide, 5 atoms. And at that thickness, the electrons stopped respecting the insulator. They tunneled straight through it. Not occasionally, continuously, in a steady leakage current from the gate into the channel. And the leakage rose by roughly a factor of 10 for every additional 2 or 3/10 of a nanometer removed. You cannot build a computer on an insulator that does not insulate. The chip burns power doing nothing, heats up, and eventually stops working. The scaling of silicon dioxide, which had driven the industry for 30 years, simply hit a wall, and the wall was a term in an exponent that had been sitting in Schrödinger's equation since 1926. The industry's escape was materials science rather than physics. Intel's 45 nanometer process, introduced in 2007, replaced silicon dioxide with a hafnium-based dielectric. Hafnium oxide has a dielectric constant of around 20, compared to silicon dioxide's 3.9, which means a physically thicker layer of hafnium oxide delivers the same electrical effect as a thin layer of glass. And a thicker barrier is exponentially harder to tunnel through. Gate leakage fell by more than a factor of 100. Gordon Moore, whose name is on the scaling law that was about to break, called it the biggest change in transistor technology since the late 1960s. Moore's law got roughly another decade because engineers found a way to fatten a wall that quantum mechanics was punching through. The problem has not gone away. It has moved. As channel lengths approach a few nanometers, electrons begin tunneling directly from source to drain, bypassing the gate's control entirely, and there is no clever dielectric that fixes that. The channel is the channel. This is one of the hard physical flaws underneath everything the industry does now, and it is why transistors stopped being flat. FinFETs, introduced by Intel at the 22 nanometer node in 2011, stand the channel up as a fin, so the gate can wrap around 3 sides of it. Gate-all-around nanosheet designs, in production from around 2022, wrap it around all four. Each redesign is an attempt to keep electrostatic control at dimensions where an exponent is trying to take it away. The node numbers you see in marketing no longer correspond to any physical measurement on the chip, but the constraint underneath them is entirely physical, and it is this one. Now the other face, which is more fun. Consider what happens when you take a photograph. The image ends up in flash memory, and flash memory works by trapping electrons on an isolated piece of conductor called a floating gate, completely surrounded by insulator. Electrons sitting there shift the threshold voltage of a transistor, and that shift is the stored bit. To write the bit, you have to get electrons onto an island that is surrounded by an insulator on all sides. There is no wire to it. There cannot be, or the charge would leak away. So the way you write to flash memory is by applying a strong electric field that tilts the barrier and forces electrons through the insulator by tunneling, the exact mechanism Fowler and Nordheim described in 1928. Erasing does the same thing in reverse. And then, the moment the field is removed, the electrons are stuck there, because now the barrier is untilted and thick, and the odds of tunneling back out are very small. Very small, but not zero, which is why flash memory has a retention specification. 10 years is the usual figure for consumer devices. That number is not a manufacturing tolerance or a warranty term. It is a statement about a tunneling rate. Every photograph on your phone is being held in place by an improbability, and slowly, over years, the improbability is losing. The scanning tunneling microscope takes the exponential and turns it into an instrument. Gerd Binnig and Heinrich Rohrer built the first one at IBM's Zurich laboratory in 1981. The design is almost crude. Bring an extremely sharp metal tip within about a nanometer of a conducting surface. Apply a small voltage and measure the current that tunnels across the vacuum gap. Because the current falls by roughly a factor of 10 for every angstrom of extra separation, the measurement is savagely sensitive to distance. Move the tip a tenth of an atom's width further away, and the signal drops by an order of magnitude. That sensitivity is what lets it see atoms. The current is so dominated by the single closest atom on the tip that the instrument effectively probes the surface one atom at a time. Binnig and Rohrer received the Nobel Prize in 1986, only 5 years after building it, which is close to unheard of. Then in 1989, Don Eigler and Erhard Schweitzer at IBM's Almaden laboratory used one to do something nobody had done before. They cooled a nickel surface to 4 Kelvin, scattered xenon atoms across it, and used the tip to drag 35 individual atoms into position, one by one, spelling out the 3 letters I, B, and M. It is a corporate logo, and it is also the first time in the history of the species that human beings arranged individual atoms by hand. They did it with an instrument that works because electrons appear where they should not. The most consequential device of all came from a graduate student who was 22 years old. In 1962, Brian Josephson at Cambridge predicted that if you place a very thin insulating barrier between 2 superconductors, the paired electrons that carry superconducting current, Cooper pairs, would tunnel across it coherently. A current would flow with no voltage applied at all, and if you did apply a voltage, the current would oscillate at a frequency determined purely by that voltage and 2 fundamental constants. He was right on every count. He shared the Nobel Prize in 1973 with Leo Esaki, who had built the first tunnel diode out of heavily doped germanium in 1957, and Ivar Gieva, who had measured the energy gap of a superconductor by electron tunneling in 1960. 2 consequences of Josephson's prediction are worth naming. The first is that the volt is now defined through it. Because the oscillation frequency depends only on the voltage and on twice the electron charge divided by Planck's constant, a Josephson junction is a perfect voltage-to-frequency converter, and frequency is the quantity we can measure more precisely than anything else. The Josephson constant is fixed at 483,597.8484 GHz per volt. Every calibrated voltage measurement made anywhere on Earth is ultimately traceable to pairs of electrons tunneling through an insulator. The second is that most of the large quantum computers built so far are made of Josephson junctions. A superconducting qubit is, at its heart, a circuit containing one, and the junction's peculiar nonlinear behavior is what makes it possible to isolate two energy levels cleanly enough to call them a 0 and a 1. Take a moment with that. The same effect that ended one era of computing by leaking through gate oxides is the mechanism on which the proposed successor is being built. The list keeps going. SQUIDs, superconducting quantum interference devices made from Josephson junctions, are the most sensitive magnetometers ever constructed, capable of detecting fields at the femtotesla level, around a billionth of the Earth's magnetic field. They are sensitive enough to record the magnetic fields produced by neurons firing inside a living human brain, through the skull, without touching it. The read heads in hard drives use tunneling magnetoresistance. The smoke detector on your ceiling contains americium-241, which has been alpha decaying, which is to say, tunneling, since long before the house was built, and will still be doing it long after. There is one last item on that list, and it closes a loop rather neatly. In 1978, engineers at Intel were troubled by memory chips that occasionally, unpredictably, flipped a bit, errors that appeared and vanished with no hardware fault behind them. The cause turned out to be trace amounts of radioactive contamination in the ceramic packaging of the chips themselves. Alpha particles were being emitted, striking the silicon, and depositing enough charge to corrupt a stored value. So an alpha particle, which escaped its nucleus by tunneling, was reaching across a few millimeters of packaging to corrupt data that was being held in place by a different tunneling barrier. The effect was quietly sabotaging its own applications. So the same effect that lights the sun is why your phone stopped getting faster the way it used to, why your photographs stay where you put them, why we can see individual atoms, and why the volt has a definition. Everything we have said so far, though, rests on one assumption. We have been talking with great confidence about the rate at which protons fuse in the core of the sun, and there is something about that number I have not told you. Nobody has ever measured it. The first step of the proton-proton chain is the reaction that produces, essentially, all of the sun's energy, and therefore all of the energy that has ever supported life on this planet. It has never been observed in a laboratory, not once, and it almost certainly never will be. The reason is the cross-section, the effective target size a particle presents for a given reaction. For proton-proton fusion, at the energies found in the solar core, that cross-section is of the order of 10 to the minus 47 square centimeters. To give you a sense of how small that is, the geometrical cross-section of a proton itself is about 10 to the minus 26 square centimeters. The reaction cross-section is smaller than the particle by 21 orders of magnitude, because the reaction requires both a tunneling event and a weak interaction event, and each of them is throttling the odds independently. No terrestrial experiment can detect an interaction that rare. You would need a beam of protons so intense, and a target so dense, that both would vaporize long before you accumulated a single count. So the rate of the reaction that keeps you alive is not measured. It is calculated, derived from the theory of the weak interaction and constrained indirectly by other measurements. The single most important number in stellar physics is a piece of theory. That is not for want of trying, and the effort involved in measuring the reactions we can measure is genuinely impressive. Under 1,400 meters of rock, at the Gran Sasso facility in central Italy, there is a particle accelerator. It is small by modern standards, and it is buried under a mountain, not because it is dangerous, but because it is delicate. The laboratory is called LUNA, the Laboratory for Underground Nuclear Astrophysics, and its entire purpose is to run nuclear reactions at genuine stellar energies. At those energies, the reaction rates are so low that cosmic rays striking the detector produce far more signal than the reaction itself. The mountain is there to make silence. In 1998, LUNA measured the helium-3 plus helium-3 reaction, a later step in the proton-proton chain, directly inside the solar gamma window. That was the first time any reaction had been measured at the energies at which it actually occurs inside a star. In 2004, they remeasured the nitrogen-14 proton capture reaction, which is the bottleneck of the CNO cycle, and found the rate to be roughly half the previously accepted value. That single correction propagated outward through the models and changed the calculated ages of globular clusters, which in turn shifted a lower bound on the age of the universe. A measurement made in a hole under an Italian mountain moved the age of everything. But for the first step, the one that matters most, the only evidence available comes from neutrinos, because they are the only things that get out of the core intact and quickly. A neutrino, produced by a fusion event in the Sun's center, leaves the entire star in about 2 seconds. The light produced by the same event takes tens of thousands of years. If you want to know what is happening in the core right now, neutrinos are the only witnesses. Which brings us to a gold mine in South Dakota. Go down the shaft at Homestake. 4,850 feet of rock above you, nearly a mile, and the temperature rising as you descend. At the bottom, in a chamber cut out of the rock, there is a steel tank the length of a bus. It holds 100,000 gallons of perchloroethylene, which is dry cleaning fluid. That is the detector. It is 1968, and the man responsible is a chemist named Raymond Davis Jr. The mile of rock is there to absorb everything except neutrinos. The tank is there because, very occasionally, a neutrino will strike a chlorine atom in the fluid and convert it into a radioactive atom of argon. So every few weeks, Davis bubbles helium through 100,000 gallons of solvent to sweep out any argon atoms that have appeared, collects them, and counts them in a proportional counter. He is counting individual atoms, 17 of them, in a typical run. That is the harvest of 2 months of the sun shining on 100,000 gallons of dry cleaning fluid a mile underground. 17 atoms, isolated from 10 to the 31st molecules of solvent, and counted one at a time. And the number is wrong, consistently, persistently, run after run, year after year. Davis finds about a third of the neutrinos that theory predicts. The theory in question belonged to John Bacall, and this is where the human part of the story sits. Bacall had built the standard solar model, an extraordinarily detailed calculation of the sun's interior structure, its temperature profile, its composition, its reaction rates, and the resulting flux of neutrinos at Earth. It was the most careful piece of stellar modeling anyone had produced, and an experiment in a gold mine said it was wrong by a factor of 3. For more than 30 years, Bacall was the man whose sums did not add up. The default assumption across the community was that the theorist had made a mistake somewhere, because the alternative was that something was wrong with neutrinos, and nothing was supposed to be wrong with neutrinos. He went back through the model repeatedly. He refined the opacity calculations, the composition, the cross-sections. The discrepancy did not move. It sat there, in the literature, for 3 decades, with his name attached to it. Other detectors were built, and made the problem worse, rather than better. Gallium-based experiments, SAGE in Russia and GALEX at Gran Sasso, were sensitive to lower energy neutrinos than chlorine was, which meant they could see the low energy neutrinos from the very first step of the chain. They also found a deficit, so it was not an artifact of Davis's method. The resolution came in 2001 and 2002 from the Sudbury Neutrino Observatory in Ontario, 2 kilometers underground in an active nickel mine. SNO used heavy water rather than ordinary water, which gave it a crucial ability. It could detect all three flavors of neutrino, not just the electron neutrinos that chlorine and gallium responded to. And when SNO added up the total flux across all three flavors, the number was exactly where Barkal had put it. The neutrinos had not gone missing. They had changed flavor on the way out, oscillating from electron neutrinos into muon and tau neutrinos, which the earlier detectors were blind to. Barkal's model of the sun had been right the entire time. The particles had been the ones misbehaving. There is a further consequence worth noting. Neutrino oscillation requires neutrinos to have mass, and the standard model, as originally written, says they have none. So the resolution of the solar neutrino problem is also the first solid evidence for physics beyond the standard model, a discovery that arrived as a byproduct of trying to work out why a man's arithmetic about the sun looked wrong. Raymond Davis received the Nobel Prize in 2002 at the age of 88, sharing it with Masatoshi Koshiba. Takaaki Kajita and Arthur MacDonald received one in 2015 for the oscillation work. John Barkal never received a Nobel Prize. He did live to see himself vindicated, which is more than many people in this story got. He died in 2005. And then, in 2014, the last gap closed. The Borexino experiment at Gran Sasso, 300 tons of the most radio-pure liquid ever manufactured, inside a nylon sphere, inside a steel sphere, lined with photomultiplier tubes, inside a water tank, under that same mountain, reported in Nature the first direct detection of neutrinos from the proton-proton reaction itself. The very first step, the one that cannot be measured in any laboratory. Borexino counted the neutrinos it produces, and the flux matched the standard solar model. In 2020, the same detector reported neutrinos from the CNO cycle, confirming a mechanism proposed by Bethe and von Weizsäcker in 1938. The measured proton-proton neutrino flux came out at about 6 times 10 to the 10th per square centimeter per second, within roughly 10% of what the model predicted. And to get a measurement that clean, Borexino's builders had to manufacture the most radio-pure substance that has ever existed, a liquid scintillator with uranium contamination down around 10 to the minus 19 grams per gram. That is not 1 part in a billion, or a trillion. It is roughly 1 uranium atom for every 10 million billion other atoms. They had to build a material cleaner than anything in nature in order to hear a whisper from the middle of a star. While all of that was happening, the solar neutrinos themselves were doing something worth a line of their own. The flavor change is not simply a free oscillation in empty space. Inside the dense matter of the solar interior, the conversion is amplified by an effect named for Mikheyev, Smirnov, and Wolfenstein, which is why the size of the observed deficit depends on the neutrino's energy. The particles were altered on their way out by the very medium whose properties we were trying to infer. So when you occasionally encounter the claim that we do not really know what powers the sun, the answer is short. We have looked inside it. Not with light, which takes 100,000 years to crawl out and tells you only about the surface, but with the particles created at the moment of fusion, which arrive here 8 minutes later, carrying an unaltered record of an event at the center of a star. The reaction that cannot be reproduced on Earth has been watched happening 93 million miles away, 1 particle at a time. Everything now checks out. The mechanism is confirmed, the rate is confirmed, the consequences are visible in the sky and in your own body, which leaves exactly one thing unresolved, and it is the thing at the very center. Here is the question. A particle goes into a barrier on one side and comes out on the other. How long does it spend inside? That is it. That is the whole question. It requires no advanced training to ask. It sounds like the sort of thing that ought to have been settled in about a week, and it has been open for 94 years. The first person to look at it seriously was Leslie McColl, who published a paper in the Physical Review in 1932, 4 years after Gamow explained alpha decay. McColl worked through the wave packet mathematics and concluded that there was no appreciable delay. The transmitted wave appeared on the far side, essentially without lag. You might read that as a tidy answer. It is not an answer, it is the beginning of the problem, because a barrier has a width. If a particle crosses a finite width in no measurable time, the implied speed is not fast, it is infinite, and whatever quantum mechanics is willing to do to your intuitions, relativity has views about infinite speeds. 30 years later, it got worse. In 1962, Thomas Hartmann, working at Texas Instruments, publishing in the Journal of Applied Physics, analyzed the delay experienced by a wave packet tunneling through a rectangular barrier. For thin barriers, the delay grows with thickness, exactly as you would expect. But past a certain thickness, the delay stops growing. It saturates. It sits at a constant value and stays there no matter how much thicker you make the wall. Think about what that implies. Make the barrier twice as thick, and the transmitted pulse arrives at the same moment it did before. Twice the distance, the same time, and therefore twice the speed. Make it 10 times thicker, and the implied speed is 10 times higher. There is no upper limit anywhere in the mathematics. This is the Hartmann effect, and it has been reproduced in several different physical systems. The experiments arrived in the 1990s, and they were not subtle. In 1993, Ephraim Steinberg, Paul Kwiat, and Raymond Chow at Berkeley published a paper in Physical Review Letters describing a beautiful experiment with single photons. They sent photons at a barrier, a multi-layer dielectric mirror 1.1 micrometers thick, and used a 2-photon interference technique to compare the arrival times of photons that tunneled through the barrier against photons that traveled the same distance through air. The tunneling photons arrived first. The effective speed came out at about 1.7 times the speed of light. Around the same time, Günther Nimtz in Cologne was doing microwave versions of the same experiment, and he went further. In the demonstration that made this famous outside physics, he encoded a recording of Mozart's 40th onto a microwave carrier, sent it through a tunneling barrier, and reported that it had travelled at 4.7 times the speed of light. He then, on more than one occasion, played the recording at conferences. So does information travel faster than light through a barrier? The consensus answer is no, and the reasoning is worth following, because it is more interesting than a flat denial. A barrier is a filter. It does not transmit a pulse. It transmits a heavily attenuated fragment of a pulse, and it preferentially transmits the leading portion. Imagine a wave packet as a hump, a rising edge, a peak, a falling edge. The barrier absorbs and reflects most of it, but what gets through is drawn disproportionately from the front. So the transmitted hump is a reshaped remnant, and its peak sits earlier in time than the original peak would have. Nothing overtook anything. The barrier simply threw away the back of the pulse, and what remains has its center of gravity further forward. There is a rigorous version of this. Sommerfeld and Brillouin proved in 1914 that the very front edge of any wave in any medium always travels at exactly the speed of light in vacuum, no more, no less, regardless of what the medium does to the rest of the wave. And since the front edge is where any new information would have to live, no signal can outrun light no matter how strange the peak's behavior looks. Herbert Winful, in a long review in Physics Reports in 2006, pushed the argument further and suggested that the entire idea of a tunneling delay has been misinterpreted. What is being measured, he argued, is not a transit time at all. It is the lifetime of energy stored in the barrier region, how long the barrier holds charge or field before releasing it. That quantity naturally saturates with barrier thickness, because beyond a certain depth the barrier is not storing any more energy, which explains the Hartmann effect without anything traveling anywhere. That view is widely held. It is not universally held, and papers arguing the point continue to appear. But underneath all of this sits a problem that is not experimental at all, and it is the reason the question has resisted 94 years of attention. Quantum mechanics does not contain a proper quantity corresponding to the time something takes. Position is an observable. There is an operator for it, and measuring it gives you a number. Momentum is an observable with an operator. Energy is an observable with an operator, the Hamiltonian. Time is not. Time appears in the Schrödinger equation as a parameter, the thing everything else evolves with respect to, and it does not have an operator of its own. Wolfgang Pauli argued in 1933 that this is not an oversight, but a necessity. If energy is bounded below, if there is a lowest possible energy state, which there is, then no self-adjoint time operator conjugate to it can exist. The mathematics forbids it. The consequence is severe. When you ask how long a particle spent inside a barrier, you are asking for a quantity that the theory does not natively supply. So physicists have constructed definitions instead. Operational, sensible, well-motivated definitions of what one might reasonably mean by the duration of a tunneling event. There are at least a dozen of them. There is the phase time, derived from how the transmitted wave's phase shifts. There is the dwell time, obtained by asking how much probability density sits inside the barrier at any moment and dividing by the incoming flux. There is the Larmor time, which uses a particle's spin precession as a clock. There is the Buttiker-Landauer traversal time, based on oscillating the barrier and seeing at what frequency the particle stops being able to follow. There are Salecker-Wigner clock times, Pollack-Miller times, and others. They are not competing approximations to a single true value. They are different questions wearing similar clothing, and they give different answers, and there is no agreed principle for deciding which one is the question you actually meant. The experiments have inherited the same disagreement. Over the last 2 decades, the most active approach has been the attoclock. The idea is elegant. You ionize an atom using a laser pulse whose electric field rotates in a circle so that the direction the field is pointing acts like the hand of a clock. The angle at which the electron finally emerges tells you when it left, with a resolution of a few attoseconds. An attosecond is 10 to the minus 18 seconds. The ratio of an attosecond to a second is roughly the ratio of a second to the age of the universe. In 2008, Patricia Eckel and colleagues at ETH Zurich published attoclock results in Science for Helium and found a tunneling delay consistent with 0, with an upper bound of a few tens of attoseconds. In 2014, Alexandra Landsman and colleagues published in Optica and reported a finite, non-zero delay. In 2019, Satya Sainath and colleagues published in Nature an attoclock measurement on atomic hydrogen, the only atom whose behavior can be modeled exactly without approximation, and found a delay consistent with 0, arguing that the earlier non-zero results were artifacts of how the residual Coulomb field of the ion distorts the departing electron's path rather than genuine tunneling delays. That did not settle it either. The most direct measurement so far came in 2020, and it is a satisfying piece of work, partly because of who did it. Ramon Ramos, David Spearings, Isabel Rasico, and Ephraim Steinberg at the University of Toronto published in Nature a Larmor clock experiment. The same Steinberg from the 1993 photon experiment, 27 years older, still asking the same question. Their approach: take rubidium-87 atoms and cool them to around a nanokelvin, 1 billionth of a degree above absolute 0. until their wave packets swell to several micrometers across, comparable in size to the barrier itself. Make the barrier out of a tightly focused laser beam about a micrometer wide, which the atoms find repulsive. Then apply a small magnetic field only inside the barrier region. Because the atoms have spin, and spin precesses in a magnetic field, the amount of precession an atom has accumulated when it emerges is a direct physical record of how long it actually spent in there. The atoms carry their own stopwatch. They measured a finite traversal time on the order of 0.6 of a millisecond, and they found something that has no classical analog at all. Slower atoms spent less time inside the barrier than faster ones. Read that again. The atoms that approached more slowly came out having spent less time in the wall. There is no version of that sentence that makes sense if you are still picturing a small object making its way through a thickness of material. It would be reasonable at this point to file the whole argument under interesting but academic. It is not academic. Attosecond timing is exactly the regime in which the newest generation of laser physics operates. High harmonic generation, laser-driven electron sources, the emerging attempts at electronics that switch at petahertz rather than gigahertz frequencies. All of them involve electrons being pulled out of matter by strong fields, which is to say, all of them involve tunneling, and all of them require you to know when the electron left. The disagreement about tunneling time is not a philosophical footnote. It is a live uncertainty sitting in the middle of a working field. There is one more line of attack worth mentioning, because it points at where this is going. Over the last 15 years, experimenters have developed a technique called weak measurement, which extracts a tiny amount of information from a quantum system, so little that it barely disturbs it, and then averages the results over enormous numbers of repetitions. In 2011, a group in Toronto used it to reconstruct the average trajectories of photons in a double-slit experiment, producing something that looks remarkably like a map of paths through an apparatus where paths were not supposed to exist. Applying the same approach to tunneling is an obvious next step, and it is being pursued. Whether an averaged weak measurement trajectory tells you anything about what an individual particle did is itself contested, which means the technique may end up producing a very precise answer to a question nobody can agree the meaning of. Take a breath here, because this is the part of the night where the ground gets soft. We have spent well over an hour building something solid, a mechanism, a history, a chain of consequences reaching from the core of a star to the cells in your arm. All of that stands. None of it is in doubt. What is in doubt is something smaller and much closer to the center, and it does not get resolved by knowing more. So where does that leave us, after 94 years? There is a well-defined mathematical theory that predicts the outcome of every tunneling experiment anyone has performed, to whatever precision they can measure. And when you ask it the simplest possible follow-up question, how long, it does not decline to answer. It gives you 12 answers, and they disagree. That would be uncomfortable enough on its own. But there is a harder question sitting underneath it, and it is the one I have been putting off all night. The harder question is not how long, it is what. What is the particle doing while it is inside the wall? Go back to the mathematics we built in the third part of tonight, and look at it more carefully than we did then. In front of the barrier, the wave function oscillates. It has a wavelength. It has a phase that advances as you move along it. Those are the mathematical signatures of something propagating, of a wave that is going somewhere. Inside the barrier, all of that is gone. There is no oscillation. There is no wavelength, because the function does not rise and fall. There is no phase advancing with distance, because there is no phase to advance. What there is instead is a smooth, real, decaying exponential, a curve that gets smaller and does nothing else. The formal way physicists say this is that the momentum inside the barrier is imaginary. That phrase gets used casually, and I want to unpack it, because it is not a technicality. Momentum is mass times velocity. If the momentum is imaginary, then there is no real velocity to assign, not zero, not small, not unmeasured. There is no number, of the kind that describes how fast things move, that belongs to a particle inside a barrier. Classical wave physics has an exact parallel, and it is instructive. When light undergoes total internal reflection, there is a field just outside the reflecting surface, decaying exponentially into the region where the light cannot propagate. It is called an evanescent field. It is entirely real. You can detect it, and it is how the two-prism demonstration works. And nobody, in the whole of optics, describes an evanescent field as something traveling. It does not travel. It exists, decaying, in a region where propagation is not possible. Apply the same reading to matter, which is what the mathematics is actually telling you to do, and you get a description that I find genuinely difficult to hold on to. A particle is detected on one side of the barrier. Later, a particle is detected on the other side. In between, there is a mathematical object that does not describe motion, no speed, no path, no position advancing with time. Nothing crossed, something arrived. Stand at the edge of that barrier for a moment with the full apparatus of physics in your hands. You have the equation, you have the boundary conditions, you have the transmission coefficient, and you can compute the probability of arrival to as many decimal places as your patience allows, and it will be right. Now ask the equation to tell you what the particle is doing, 3 atomic layers into the wall, and the honest answer is that the question has no referent. There is no particle 3 layers into the wall. There is an amplitude. It is a number attached to a location, shrinking with depth, and there is nothing in it that corresponds to a thing being anywhere. The wall is not solid to a wave. That is the sentence I gave you an hour and a half ago, and I want to take it back now, because it was too generous. It suggested there is a wave inside the wall, passing through, thinned but intact. There is not. Inside the wall, there is no wave in any ordinary sense. No crests, no troughs, no motion, nothing going anywhere. The image you have been carrying since the third part was a scaffold, and this is where it comes down. What replaces it depends on which physicist you ask, and they do not agree. On the standard, minimal reading, the question is simply not a physics question. Quantum mechanics predicts the outcomes of measurements. There is no measurement of the particle inside the barrier, so there is nothing to say, and asking what happens between detections is like asking what a coin is doing while it is not being looked at. On a pilot wave reading, in the tradition of de Broglie and David Bohm, the particle does have a definite position at every moment and does genuinely cross, guided by the wave. And curiously, the Bohmian calculation reproduces the Hartmann effect without anything moving faster than light, because the particles that get through are the ones that happen to start closest to the far side. On a many worlds reading, all outcomes occur, and the probability is the weight of a branch. On time-symmetric readings, influences propagate both forwards and backwards from the measurement, and the idea of a duration inside the barrier becomes even harder to pin down. It is worth being fair to the first of those positions, because it is often mistaken for intellectual laziness, and it is not. The claim is not that the question is uninteresting. The claim is that physics is in the business of predicting what instruments do, that no instrument has ever registered a particle inside a barrier, and that a theory which stayed silent about unobservable intermediate states is behaving correctly rather than failing. On that view, the discomfort you may be feeling right now is a symptom of expecting the world to be made of little objects, and the cure is to stop expecting it. That is a coherent position, held by people who understand the mathematics better than I do. I am not sure I can hold it for more than about a minute at a time. Every one of those pictures gives the same numbers. Every one of them is held by serious people who have thought about it for decades. and no experiment anybody knows how to build distinguishes between them. So here is where we end up. We can calculate the rate of quantum tunneling to 14 decimal places. We can measure it, engineer it, exploit it, build industries on it. We can trace it from the core of a star to the electrons crossing your mitochondria while you lie there. And we cannot say what happens. Have not yet said. Cannot. The most successful theory ever constructed by human beings, tested more precisely than any other idea in history, has nothing to offer about the middle of the process that makes existence possible. The effect is not confined to stars and cells, either. It may bracket the whole thing. In 1982, Alexander Vilenkin published a short paper in Physics Letters B with the title Creation of Universes from Nothing, and developed the idea over the following 2 years. The proposal treats the size of the universe itself as the tunneling coordinate. Between a state of zero size, no space, no time, no matter, and a universe large enough for inflation to take hold, there is an energy barrier, and the calculated probability of tunneling across that barrier is not zero, even starting from nothing at all. The rival proposal from James Hartle and Stephen Hawking in 1983 uses a different boundary condition and gives different answers, and the two have been argued over for 4 decades without resolution. I want to be clear that this is speculation with equations attached. It is untested and, on current understanding, close to untestable. Then there is the other end. The measured mass of the Higgs boson, around 125 gigaelectronvolts, and of the top quark, around 172.5, place the vacuum of our universe in a region of parameter space that is metastable rather than stable. If that holds, then the vacuum we live in is not the lowest available state. There is a lower one, behind a barrier. And a barrier, as we have spent all night establishing, is not a prohibition. Andreasen, Frost and Schwartz calculated the expected lifetime in Physical Review D in 2018 and got a figure of the order of 10 to the 139 years. The universe is around 10 to the 10 years old, so this is not something to lie awake over, and the calculation assumes no new physics at all between here and the Planck scale, which is an assumption almost nobody actually believes. But notice the shape of the sentence. Statistically impossible, not physically impossible. I said that about your hand and the wall beside your bed, and it was reassuring. Applied to the stability of physical law itself, the identical sentence stops being reassuring, and not one word of it has changed. Only the subject has. There is a version of Hawking radiation, published by Maulik Parikh and Frank Wilczek in 2000, in which black holes evaporate because particles tunnel out through a barrier created by the geometry of space-time. So even the slow disappearance of black holes can be written as a barrier problem. The origin, the present, the end, all three, on our current best guesses, are barrier crossings. And the light from the barrier crossing nearest to you takes 8 minutes and 20 seconds to arrive. That number seemed like trivia when I mentioned it earlier tonight, and I want to put it back in place now. 8 minutes and 20 seconds is the last and shortest leg of the journey. Before that, 100,000 years of stumbling outward through the body of the sun. And before that, an event which took no time anybody can agree on, involving nothing anyone can describe, in which 2 particles that could not reach each other simply did. That is what is happening above your head every day of your life. That is what warmed the water you drank, and grew the food you ate, and assembled the atoms you are made of. This is the reason life exists, and almost nobody has been told, and the people whose job it is to know cannot tell you what it is. I have spent a lot of nights with strange ideas, and this one still stops me. Not because it is frightening, because it is so quiet about itself. There is no drama in it, no violence, nothing to see. 2 protons approach a wall they cannot climb, and then they are through, and 8 minutes later, somebody on a small planet feels warm. Thank you for spending this time with me, and for going the long way around the physics of quantum tunneling. If this is the kind of exploration you like to fall asleep to, a like or a subscribe would mean a great deal. It helps me keep making these. And remember, the next time sunlight lands on your face, that it is the receipt for something that could not happen. Good night, and may you never look at a solid wall quite the same way again.